Welcome to a brand new episode of Dave Does Math from Home. Today we are talking about section 2.5. We're doing function transformations. So function transformations means we're taking a function. Basically, we're taking the graph of a function and we're messing with it a little bit. Usually that involves scooting it around. We're going to shift things back and forth. We'll shift things up and down. Sometimes we'll stretch it. Sometimes we'll squish it, or stretch it vertically, squish it vertically. Sometimes we're going to flip it. That's basically all we're doing. Shifts, stretches, flips. That is the entire point of this function. So we're just, the entire point of this section. We're just going to mess around with some graphs. The two graphs that I want to mess with, I think the two graphs that are sort of most easily accessible and easy to mess with for this section are, I'm going to be, I don't have enough board space to like leave these here. So I'm going to create some functions here, sketch some graphs, and then I'm going to erase them. Please put these functions and their graphs and their tables into your notes so that when I reference them later in the video, you know what I'm talking about. The two functions I want to mess with today are f of x equals x squared and g of x equals the square root of x. X squared, if I want to make a table of values, goes -2, -1, 0, 1, and 2. Turns into 4, 1, 0, 1, 4. And the graph for that is parabola. So here's the 5 points on my table. Does this. If I want to make a table for g of x, it would look like, the table for g of x means that you have to choose your x values much more carefully. You want to choose x values that have nice, easy, reasonable square roots. So we're going to go 0, 1, 4, and 9 are the 4 that I want to use. The square roots of these things are 0, 1, 2, and 3. So this graph, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 0, 0, 1, 1, 4, 2, 9, 3. This graph looks like this. It's kind of half of a parabola sideways. We flipped it around. So these are the two, let me block some glare. These are the two graphs that I'm going to be playing with for the rest of this section. Put this in your notes somewhere so you have it easily accessible. And then we'll talk about transforming them. Okay, the first transformation I want to do is I want to look at what happens if I do f of x equals x squared plus 3. Hopefully, this is the kind of thing where you can sort of guess what might happen to the function when we do this transformation on it. If you just slap a plus 3 on the end of this function, maybe you can guess what will happen, maybe not. The good news is, if you can't guess what's going to happen here, figuring out what's going to happen here is relatively straightforward. We're just going to make a new table of values. X squared plus 3. When I make tables of values for function transformations, I just add additional columns. That helps me keep everything organized. So the thing I like about add additional columns plan is that these two columns are exactly the same as they were for the base function. X and x squared, 4, 1, 0, 1, and 4. It's all fine. I'm just going to add a third column here where I take these same values from the base function and I add 3 to them to get 7, 4, 3, 4, and 7. So when I draw this graph, 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7. The original, the base function, is still here. There we go. This is still the base function, y equals x squared. The transformed function is going to go 7, 4, 3, 4, 7. So the transformed function has all the same values as this function. They're just shifted up 3 units. So because of that, we say that this transformation is a vertical shift up 3. Hopefully it's not too much of a stretch to imagine that g of x equals x squared minus 4 would be the same thing, but shifted down 4 units. 4, negative 3, negative 4, negative 3, and 0. So this is y equals x squared minus 4. This is y equals x squared plus 3. So this one just means down 4 units. So that's what's happening here with vertical shifts up and down. You could do this to a square root function as well. If f of x equals the square root of x and you wanted to explore what happens with g of x equals the square root of x plus 2, one of these would look like the standard square root function. The other one would look like the square root function plus 2. We're just taking the whole shape and moving it upwards. So that is vertical shifts. You could go down with this as well. It's now time to talk about a different kind of shift. So next I want to talk about, let's say f of x equals the square root of x minus 3. This is a slightly more interesting kind of transformation because instead of this addition or subtraction piece happening after the function has already done its thing, like outside the function, this is now happening inside the function. I've got this minus 3 inside the radical here. So for this, I'm going to make another table, but this time I'm going to put the extra column of the table in the middle. So I still have a 3-column table. But I have the transformation happens in the second column, and then the function happens in the third column, which is a little different than the last table we had. Our inputs, our function was in the middle, and then the transformation was at the end. Here, because the transformation is on the inside, we have to put it in the middle. So input, transformation, then the function. And when you're filling out a table of values like this, I always start in the middle. So this is the step where the base function happens. This, from between this column and this one, this is where we're going to actually perform the base function, take the square root of things. Because of that, I want these numbers to be the ones that are really nice numbers to take the square roots of. So I want these numbers to be my 0, 1, 4, and 9 from the old table. I'm putting those right in the middle. I'm not going to start with those numbers. If you started with 0 here, then this column would be negative 3, and then you'd try to take the square root of negative 3, and you'd have a big problem. So the numbers that I actually want to take the square root of, I put those numbers in the middle. And then the square roots of them are nice and easy. 0, 1, 2, 3. That hasn't changed. But But now the thing is, I have to go backwards to get the original inputs. If I want x minus 3 to equal 0, that means that the x value I needed to have started with was 3. So to do this, I have to add 3 to whatever this is to get the original x value I wanted. Here I have to add 3. So if I want x minus 3 to be 1, that means that x had to have been 4. If I want x minus 3 to be 4, that means x had to have been 7. And if I want to subtract 3 and get 9, that means I need to start with 12. So to go backwards, you have to add 3 to all of these things to sort of undo this transformation that happened to make these numbers what we wanted. Because these inside the function transformations happen before the function, and we have to sort of undo them to get the original inputs, these transformations have sort of the opposite effect you'd think they would. Well, let me sketch a graph of this, and then we can talk about what kind of effects they do and don't have, or what you may have expected. Graph first, then talking. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3. I only need to go up to 3 on the y-axis. So the base function is still 0, 0, 1, 1, 4, 2, 9, 3. Base function is still here. I missed. That's fine. It's a really big dot. No one saw that. This is still the base function. Y equals square root x. The transformed function goes 3, 0, 4, 1, 7, so 10, 9, 8, 7, 2, and then 12, 3. Base function is here. I missed that middle one again. I think I just have really bad scaling on my axis. Sorry about that. Anyway, what's happened here is that our function has moved 3 units to the right, which, going back to what I was starting to say earlier about what you may expect, you probably weren't expecting this subtraction to move things in the positive direction. When we do up and down transformations, addition makes us go up and subtraction makes us go down, and that makes perfect sense. When we do these horizontal transformations, we sort of end up going in the opposite direction that you would expect. Subtraction makes you go to the right. Addition would have made us go to the left. And the reason that these interior transformations are kind of backwards is because we have to undo them. This, going from 0 to 3, we have to add the 3 to sort of undo this transformation to get the x values we want. So this is why we start in the middle. We start in the middle column because these are the numbers that we want to do the base function on, and then we go backwards to get the original x values, and that going backwards is sort of what makes this thing backwards. That's why we go right when we subtract. If we had done something like g of x equals the square root of x plus 2, we would have still put these exact same numbers in the middle column, 0, 1, 4, and 9. But if those are my x plus 2 values, then my x values would have needed to be 2 less than that. So we'd have had to subtract 2 to get negative 2, negative 1, 2, and 7. So this would push us back 2 units. 0, 52, 52, and 7. So this would have been backwards to do this one. So this is y equals the square root of x minus 3. Minus 3 pushes us that way. This is y equals the square root of x plus 2. Positive 2 pushes us this way. So that's what happens when we do these shifts inside the function. So far, the moral of the story, I think, is when you add or subtract outside the function, that creates a vertical shift, and it goes in the direction you expect. Addition is up, subtraction is down. When you add or subtract inside the function, that creates a horizontal shift, and it goes in the opposite direction you would expect. Subtraction goes to the right, addition goes to the left. I'm going to cut this video here, and we'll pick up with what happens when you multiply things in part 2. So stay tuned.